And you'll remember that we know this story because we can actually image the seismicity caused by the friction as these plates descend, pushed into the earth or dragged into the earth. There's a frictional resistance against the crust and mantle against which they're rubbing, and that results in seismicity. So over the past 30 years, these zones, these subduction zones, have been mapped in very great detail, plunging into the earth. Now you can actually look right down to the interior of the earth above the core and see how these plates are initially rigid, then become blobby as they start to melt, and then they recirculate and come recycle back up to the ocean ridges. So geophysics is a wonderful thing.
Could you just turn around a bit, not to look at the screen? It's very difficult to hear.
Oh, okay. Well, I'm speaking into the microphone, so perhaps that's the problem. Let me move the microphone. Oh. Oh, okay. Okay, right, okay. Sorry. Okay, so that's explained the basic terminology I'll be using for the structure. So next slide, please. Okay, so now we're going to look at the subduction zone that's associated with the New Zealand side of the Pacific. And I'll be coming back to New Zealand later in the talk to make my analogy. And I'm going to compare what was happening in central Britain 565 million years ago with what's happening in New Zealand, North Island today. So that's the basic theme of the talk. Next slide, please, Gareth. Okay, sorry, we jumped 2 there. That's it. Oh, next one. Right. Time scale. We're talking about the Ediacaran. That's there. Talking about this period down here, late Precambrian times. What Peter Gutteridge will be telling you about in a week or so's time, or next lecture, is the deeper Precambrian, about 1,200 million years old. I'm going to tell you about this bit, the so-called Ediacaran, 635 to 542 million years. And that's interesting too from the point of view of fossil life, because that's the period that immediately precedes the appearance of hard-bodied fossils like trilobites, all those cute things in Cambrian times. But in the Ediacaran times, the bodies are soft. They're soft-bodied, no skeletons, no shells to be preserved as fossils. But they do leave impressions. They do leave a mark. And we'll be seeing a bit of that later. That's not my work, but it's all part of the story. So we're going to go back to about 565 million years ago, way back into the mists of time. Next slide, please. And that's when the crust of southern Britain formed. Some rock terminology here. You'll remember that basic rocks here, like basalt and gabbro, have about 50% silica, and they're called mafic rocks. We're not going to talk much about those today. There will be a few. But mainly, we're going to be talking about this spectrum here, from andesite, dacite, and rhyolite as volcanic rocks, where increasing from 45 up to 75% silica, and from gabbro up through to granite, same, they're the equivalent terms. So gabbro is equivalent to basalt, diorite is the equivalent term to andesite, which is a volcanic rock. Granodiorite is the equivalent rock term for dacite, and then finally granite, that's the deep buried equivalent of a rhyolite. So the volcanic rocks, of course, crystallize at the Earth's surface, so they're very fine grained because they get chilled quickly. Whereas this suite of rocks, what we call plutonic rocks, they crystallize deep in the Earth's crust. So the temperatures are much hotter there. The rocks have much longer to cool, so crystals grow in them much bigger. So that's the main difference: fine grained rocks, coarse grained rocks. And of course, the mineralogy varies as we get more and more silica in the rocks. Quartz does appear as a free phase, and we get more potassium feldspar, and so on. Next slide, please. Caught you on the hop there. Okay, so So this is the published geological map of Charnwood Forest, published by the BGS, my former employers. And mainly pink, as you can see, that's mainly Triassic rocks. But the pre-Cambrian sticks through. All these darker purple patches here, these are bits of pre-Cambrian rocks. But as a geological map of the pre-Cambrian, it's not very spectacular. But I will come to a better one. Next slide, please. Now, the reason that most of that map is pink is because of this stuff. This is the Trias. These are some sands, but mainly mudstones of the Mercia mudstone group of the Triassic. And basically, these are mantling a eroded desert landscape of Triassic age. So it's very spectacular. This is Barden Hill Quarry, and this is effectively a wadi cut into the desert land surface with considerable topography on it. And we know it's considerable topography because the Sherwood sandstone, which is the first part of the Trias, the lower part, for example, as seen at Nottingham Castle, that's missing here. So basically we have what we call onlat, where the Sherwood sandstone, the Triassic sandstone mantle the lower topography, and it's only the later rocks, it's only the Mercia mudstone group, the higher Triassic, that mantles the topography. So we know we're talking about an old eroded desert landscape. And it's these sort of quarries in Charnwood where you can see this. But that's the reason why the geological map is mainly pink. It's all because of this stuff, which conceals this stuff, the pre-Cambrian. Next slide, please. Looking at a more realistic map for our purposes, this is the map produced by Charlotte Kenchington and her colleagues. It's based on work by the Geological Survey. What Charlotte's done is basically strip off all the pink stuff, so you can actually see the form of the pre-Cambrian rocks in the subsurface. And you can see, this is a map, obviously, brings out the form of the Charnian anticline, and a stratigraphic section for the same. And basically, the old rocks are up here near Shepshed, just off the M1 motorway. And higher parts of the stratigraphy go through here to these rocks here. So that's basically that transition up through there to the mauve-coloured rocks up here. And that's about 2 kilometres of section. The whole Charnian stratigraphy is about 2.9 kilometres, I think. So quite a lot of stratigraphy. And you'll see from the dates that my colleague Steve Noble got back in 2015, that's about 12 million years based on very precise zircon dates. So there's a lot of rocks, 3 kilometres of stratigraphy there, deposited in 10 million years. And you'll have to take my word for it. That's quite a fast rate of deposition. So the first thing you think of is, well, why has that happened? Why is so much sediment accumulated in that time? So that's a question you can ask me later if I forget to tell you in between. Another thing you'll notice from this map, very interestingly, that it's the succession is very stratigraphic on this side of the anticline, but on this side there's all sorts of interruptions. Now these dark purple bodies, like the volcanic porphyry rocks we saw in that slide from Barden Hill here and at Whittick. And then these other things here, these South Charnwood diorites, these red bodies that cut across the stratigraphy, and they're clearly later than the bedded succession. So these purple rocks here, these are the contemporary with the sediments, and they're basically volcanic complexes, volcanic domes, intruding and extruding into the contemporary seafloor, and then producing debris flows and material within the sedimentary layers here. But these red rocks here, these are these later diorites, and they are basically intruding the sequence at a slightly later date. And the main interest for doing this paper was because of this famous Ediacaran biota. The rocks of this age, you can correlate them from here to the White Sea in Russia, to Namibia, and to South Australia. They have this very distinctive biotic assemblage, which are basically the immediate predecessors of body fossils in the Cambrian. So it's a very important time, and a lot of colleagues are doing a lot of work on these rocks because they're basically heralding multicellular life. The rocks that Peter will tell you about are probably microbial and not got many cells to them, if any, or they're just unicellular, whereas these are multicellular organisms. Next slide, please. Okay, so here I am at the famous bomb rocks in Charnwood Lodge. This is an agglomerate, as you can see, of which blocks of dacite and andesite lava, which have not come very far. In fact, they're forming a screen to those dark purple intrusive complexes I was showing you on the last slide. Next slide, please. And then the part of the Charnian that most people are familiar with are these very fine grain rocks, so-called hornstones or dust tufts, for example, on Beacon Hill and so on in Charnwood. These represent fine grain ash that's been blasted up into the atmosphere from these volcanoes and then deposited within the sedimentary sequence. So basically, this is typical Charnian sediments here, containing a greater or lesser component of volcanic ash. But because the volcanic source is so high, that's the dominant source. And that's part of the clue to why so much of the sediment accumulated. You've got very active volcanism, and it's just erupting and dumping sediment into an adjacent basin very rapidly. Next slide, please. Another feature of these rocks, this is not a very good slide because it's against the light, so it's difficult to acquire. But you can see that the bedding in the sediments is all over the place. It's all jiggly-piggly, and that's because this is a slump breccia. And these horizons of slump breccia, which represent the layered volcaniclastic sediments, which are then slumped into the adjacent basin, driven by tectonic events, possibly by earth seismicity, so on. These slump breccias form a distinctive mapping horizon, and this is the main way of actually subdividing the Charnian, because you can follow these slump breccias throughout the area. Next slide, please. And then the famous fossils that I was telling you about. This is the memorial slabs. This is John Carney leading a field trip on the memorial slabs. And on this bedding plane are these numerous, well, they used to be before they were chopped out by fossil collectors, but there are these little circular depressions which have been interpreted in various ways in the past. Next slide, please. And this is the sort of thing I'm talking about. Famous Charnia, of course, discovered by Roger Mason as a schoolboy in 1958. And then more other things that they call pizza forms, and then these circular things. These are typical components of this biota that is found worldwide. Now, I'm not a paleontologist, so I haven't explained that terribly well, but I refer you to Charlotte Kenchington's paper if you want to read more. They're fascinating things, and how these relate to the body fossils that followed immediately after in the Cambrian period is a very interesting question. Next slide, please. This is just a reminder that we're obviously here in southern Britain, but rocks of similar type are found in Newfoundland and Nova Scotia, into New Brunswick, within the Appalachian belt, down here, right down to Florida. And then on continental Europe, there's another suite of rocks that is a similar sort of age. These are referred to the so-called Cadomian suite. Again, same sort of age, but their starting position when the continents that form these rocks broke up is slightly different to these. And these rocks here are now caught up in the Caledonian origin that goes all the way from Norway through Canada to southern southeastern USA. And then these rocks here are caught up in the Variscan origin from Germany through to North Africa, Mauritanides. Next slide, please. Now, this was the first attempt I made to make a map of the terrains of this age. These, rocks in age from 542, which is the base of the Cambrian, back to about 700 million years. And this was published in 1987. And basically, I concluded that there's a fundamental dividing line in Britain, represented by what is now the Malvern Hills, which you're probably familiar with. And the terrain, there's a terrain which are called the Charnwood terrain east of that, a terrain called the Recian terrain west of that, and subsequently further discoveries led to other rocks slightly different in aspect in eastern England and in Wales. So that was the sort of picture that emerged. That's based on the lithology and age of the rocks involved. And the basic model was that these different bits of pieces of crust have been brought together tectonically by strike slip along major fault zones. Wes Gibbons started all this off by recognizing a major seismic fault zone here in the Anglesey region, separating Anglesey from the Welsh Basin. But I then sort of extended it to the Malvern lineament and to these other boundaries. So the idea was that these bits of crust were brought together by strike slip, by tectonics moving bits of crust along fault zones, bringing them into juxtaposition. That seemed to fit the mood of the times, and I didn't really need to modify this idea for till about 2000, when, next slide please, when I started to realize there were some problems with this so-called accretionary model. Accretion is the term we use for this sort of tectonics, where you move slabs of crust around, a bit like the San Andreas Fault. If I told you the San Andreas Fault, you got that in your mind, what's happening in California with coastal California moving against inland California, with a big strike slip zone which might have thousands of kilometers of displacement on it. And you may know that the Great Glen Fault, for example, in the Scottish Highlands, has, some people say 100 kilometers, some people say 500 kilometers of displacement. So there are these big fault zones, and they will juxtapose different regions of crust. That wasn't the problem, though. The problem was associated with the structures in the rocks, and the fact that the older ages were restricted to west of the Malvern line. There are no rocks older than this east of the Malvern line. And they also studied the magnetic anomalies in the crust with Mick Lee and Jack Soper, and that was problematic for the model too. And then there were these other terrains like the Fenland terrain and the Welsh terrain. These were rocks, again, of different ages. How did these fit in? So basically, we used that terrain model until the Geological Conservation Review, but I worried about it. Next, please. So when COVID struck, I had the opportunity to get away from all the other things that BGS wanted me to do, mainly about looking at seismic reflection lines. And while sitting at home, I was able to think about the Charnwood and what we knew and what we didn't know, what we needed to know to try and resolve this problem. And this was the new map that I came up with. It looks the same. It's got a yellow belt here, rocks about 600 million years. Got blue rocks here. Looks like the Charnwood terrain, doesn't it? Same blue wedge. And the stuff to the west of the Malverns looks the same. It's all orange, but I've got a few green rift structures in here with, for example, the Euraconian in. But basically, you probably think that map's the same as the last one. It's actually very different in its philosophy, and it relies much more on extensional tectonics, simple pulling apart of the crust, rather than strike-slip tectonics and accretion. One of the first things I had to look at was to review the deep boreholes because, as we've said, you got the impression from that picture of Barden Quarry, Barden Hill, that the Triassic is obliterating things on a local scale, when exactly the same thing happens on the regional scale. Most of this region here, as Stuart will confirm, is covered in the Triassic rocks. Then beneath that, sometimes Carboniferous, and so on. So that this map, which has got all these continuous, nice, firm lines on it, is in fact very speculative. All these lines should be dashed lines because we don't really know. We've got very few data points. We've got the surface outcrops, for example, at Charnwood Forest itself. We've got the nice outcrops you used to have, at least in the Nuneaton area. We've got famous Uriconian in Shropshire, and we've got the rocks of the Malverns themselves. But apart from that, and all these things are tectonically controlled by these major tectonic lineaments. Apart from that, there's very little evidence. So all these lines are very speculative, and they're drawn in tentatively on the basis of information from other sources like locations of boreholes and geophysical information like magnetic and gravity data. And the magnetic data I'll come back to because actually that's the core of my talk. But the first job was to actually look at the boreholes, and I won't bore you with these names probably. K is Kempsey, Netherton. These are deep boreholes that are in the Vale of Severn, within what geologists refer to as the Worcester Basin. In fact, the Worcester Basin is a Triassic feature. It has a much older history. These are actually sampling a pre-Cambrian basin underneath the Triassic basin. There's a complexity there, but we'll come back to that maybe. We've got another borehole here in the blue, the only one in this deep blue. It's called Withycombe Farm. That's near Banbury in Oxfordshire. And then we come to this group of boreholes over here in the Peterborough area. There, Alton, Oxenden Hall, and then near Charnwood Forest itself, we actually got the Morley Quarry borehole. That was a borehole we drilled in 1987 to investigate its geothermal potential. So those are the boreholes that I'm going to review now, and I'll tell you what the story is. Before we move on, though, I would just say that the new model here relies on all the older crust, all the older Precambrian crust, that's crust older than about 600 million years, lying west of the Malverns. The only exceptions being these green rift zones where there are rocks of 565 million years old. These are dated using zircon grains very precisely. And it turns out that those dates in these rift zones here are exactly the same as the Charnian. So that's all part of the story, which I'll pull together later. That's Heath Farm borehole in Staffordshire, North Staffordshire. That's right on the Malvern lineament. And you could actually say, well, you know, are these rocks Uriconian affinity or are they Charnian affinity? But as I'll tell you later, it doesn't make any difference. The Uriconian is the Charnian. And that's why the Charnwood terrane no longer exists. It's a domain emplaced into the older crust. But I'll come back to that. That's a younger story. I think the Lickey quartzite is, what age is that thought to be now? No, it's not. No, it's not as old as that. It's early Ordovician, yeah. So it's part of that Arenig overstep sequence, I think now. Okay, next slide, please. Okay, well, this looks a bit boring. But basically, the first bit of spade work was to get the geophysical logs from these boreholes. They've all been drilled for stratigraphic test wells or some other purpose. Some of them are survey boreholes. As I said, Morley Quarry was geothermal. Netherton was drilled as a real wildcat exploration well. That was interesting because that's the only one with an actual isotopic age. which suggested that the Netherton volcanics were actually Silurian in age. But I did my spade work. Next slide, please. And what I found was that the sonic velocity, this is in meters per second, so that's 5.5 kilometers per second, was exactly the same as, for example, Kempsey, and pretty much the same as Heath Farm, and certainly the same as Morley Quarry. So there was no doubt in my mind from the sonic velocity of these rocks. The sonic velocity reflects hardness. These are old, hard rocks. They're not Silurian, they're pre-Cambrian, and they've got the sonic velocity, the speed at which they transmit sound through the earth, is exactly the same as Kempsey or Morley Quarry near Charnwood Forest. The same thing came out of the densities as well. 2.68, 2.68, 2.68 grams per cc, exactly the same. The density of the old rocks is much greater than the younger rocks. Next slide. But the real interest is this slide that comes now. Next slide, please. Oh, thank you. Sorry, too far. Back one. There we go. Withycombe Farm, Banbury, a BGS borehole drilled in the 1960s. The interesting thing is the sonic velocity is over the 6 kilometers a second, and the density is greater. That's because it's mainly mafic rocks. So very interesting thing, this Withycombe Farm borehole is sitting between more silicic rocks, more felsic rocks with lower sonic velocities and lower densities. Okay, so what's that about then? Next slide, please. And when we look at these are the geophysical logs, or some geophysical logs from these boreholes. The standard convention is to have the gamma ray log on the left-hand side, and which measures the potassium content, and sometimes thorium and uranium, basically the radioactive elements in the core. And then on this side, we conventionally plot the velocity logs and the density logs. And basically, these are geophysical logs that a standard procedure in oil exploration. You drilled your borehole, you drop what's called a sonde down, it's like a metal sensor on a cable, and you drop that down into the borehole and then pull it back up slowly, and that then measures the physical characteristics of the rocks around the borehole. And from that procedure, by drawing that up slowly, you get this continuous log of borehole physical properties. In this case, they're looking, as I say, at the gamma ray, which measures the radioactivity, and the sonic log and the density log on the right-hand side, which measure the sonic velocity and so on. So we looked at those boreholes already. These are the two you're already familiar with. That's Kempsey and Netherton. And then we've got Morley Quarry, the Charnian representative, and then Withycombe, a very short proving you'll see here. Not much of a proving at all, but what was proved was extremely interesting. This log here is Morley Quarry again, so it's the same log as this one, but I've just expanded the graphic log to compare. You can see that these features join up across here. And what these things are, we found that in Morley Quarry, there are a number of these fining upward cycles reflecting debris flows fining up into strata that become just those dust tufts like at Beacon Hill. So in other words, we're going from coarse debris flows, which have where the sediment has slipped into the basin, probably triggered by volcanicity, a volcanic event, or an earthquake event. And then as we move up the succession, we come into finer grain sediments that are not slumped and represent the sort of background infall of volcanic dust into the section. And in Morley Quarry, we recognize a number of these things, these debris flows. These are the two best. But then when I looked at the other logs, for example, at Kempsey and Netherton, I began to see the same sort of features there coming out in the gamma ray logs. So one there, one there. So on both sides of this Withycombe farm, we've got these big, we've got silicic volcaniclastic sequences, which have got these big sedimentological evidence for these big debris flow type features forming in them. Next slide, please. Looking at some very basic chemistry here. I know most of you won't know much about volcanic geochemistry, but I'll tell you that we can analyze a rock, we can crush a rock up to powder, we can analyze it in various ways, and we can plot the data we get on this diagram, which is a triangular plot of titanium versus zirconium and yttrium. So we measure these quantities of these trace elements in the rock. And typically for zirconium and yttrium, there's only about 100 or 50 ppm in the rock. So we need to have analytical equipment that's quite precise, but most university departments have such kit to analyze rocks. And when we look at the different locations that we've studied here, we've looked at the Charnian sequence here, and we've looked at the Malvern rocks, the Malvernian rocks over there, for example, in Kempsey and Netherton borehole. They plot in this field here, B, which is a field which is a common arc field. Sorry, a common is a typical sort of back arc marginal basin type crust. If you move that way, you're becoming even more primitive. If you move this way, you're moving towards more calcalkaline volcanic arcs. And the simple story is that the Charnian rocks are actually quite primitive basaltic rocks, typical of a marginal basin. And the same thing with the Malvern rocks. So that's the two yellow borehole occurrences, if you like. Remember the green borehole that lies between them, Withycombe Farm, that's even more primitive. So the story is that that's a volcanic arc sequence sandwiched between two marginal basins. When we go to the Uriconian, west of the Malverns, and that has a rift sequence that is got a more of a continental component in, so it's probably a thicker crust. Next slide, please. And then these are what we call spidergrams. I shan't labor these, but you take it from me that these signatures reflect various salts, various components of a volcanic arc basin. So the features we look for are these particular peaks here in the rare earths like cerium and elements like thorium. They tell us we've got an enrichment that is typical of a volcanic arc. It's not that mature, it's not a continental arc, because these patterns are quite flat. Because what we've done is we've referenced these patterns against a mid-ocean ridge basalt, the stuff that forms ocean ridges, and which is one of the most primitive rocks going, and we've compared it. And you can see that some of the rocks in the Malverns are more primitive than the average mid-ocean ridge basalt. They're typical of rocks that form in marginal basins, for example, in the Japan Sea, the Marianas Trench today. So they're quite primitive rocks. The Charnian is a bit different. That has more of an arc component to it, as reflected in this increasing amount of elements like potassium, uranium, and so on, which tell us that the arc component is stronger. And the Uriconian rocks, you can see that their patterns are way above this reference line, and that's telling us that there's continental crust involved. So you can interpret that as an arc volcanic sequence, one that's formed in a continental rift in thickened crust. Anyway, we won't spend too long on that. It's all a bit detailed and specialized, but just so you get the impression that you can analyze rocks, you can determine a range of trace elements in them, you can measure them with some degree of precision, and then you can compare them with a mid-ocean ridge basalt and say a lot about the tectonic environment, the environment in which these particular rocks formed. Next slide, please. So now we come on to the meat of the talk, which is about the inversion model of aeromagnetic anomalies. And I told you that one way of trying to plot the boundaries between these different types of rocks is to use geophysical information like gravity maps or magnetic maps. And we've taken this one step further. My colleague David Beamish came up with this technique, in BGS at least. Yes, next slide, please. And basically, this is the aeromagnetic field of southern Britain. And this is produced by a plane flying repeated transects at a constant level, about 250 feet, I think it is, up and down here, measuring the magnetic field and building up a map, okay, like this. And this is, you can process this in various ways, but basically it records the magnetic intensity, the magnetic susceptibility of the rocks. And you can see that in central England, from Wolverhampton, say, running down through Banbury's about here, down to south of London, you've got this very large body of magnetic rocks, okay? And then to the north, the character of these, the rocks are still magnetic, but their character is slightly different. It's a bit like fingerprints, really, or a genetic code, a DNA code. This is a sort of technique that was actually used to identify plate tectonics and seafloor spreading in the first place, when they recorded the magnetic stripes that reflected the, spreading of the oceanic crust. Okay, next slide, please. Now, this is the technical stuff, but basically the key information here is that we're using old data and we're looking at it in a very clever way to build this model. And the model has a resolution of 1 kilometer by 1 kilometer in area and extends down 34 kilometers into the crust. So we're building up a model, and when you look at the area we've covered, it's about 275 by 225 kilometers down to 34 kilometers. That amounts to more than 2 million susceptibility points. And the other important thing to remember is that unlike a seismic model or a seismic section, where you're actually imaging a physical property directly, there's some physical structure in the earth and it responds to the signal that you put in. It gives you you're really seeing something there. With a model, a forward model, you basically depend on an algorithm. In simplistic terms, the algorithm, the computer, looks at the basic recorded magnetic data set and assigns a value to every bit of the space, every one of those cells, which it thinks is the best fit to the observed field. So we're one step away from reality. We're talking about a model here, not an actually observed physical property, but the physical property was observed in the first place, and the computer is making a decision about what it thinks the internal structure of that data set is to its best ability, and using parameters that we put in. No, that's yeah. Oh, there are components, high-res surveys that have been acquired, Anglesey, Cornwall, Tellus in Northern Ireland, but they cover relatively small parts of the country. And the problem is there's more and more infrastructure being put in, power lines and all the rest of it. It becomes more and more difficult with time. So yeah, we may be stuck with that 1965 legacy data set for years to come. Sorry? Oh, that was back in the 1960s. That was Hess and those guys. That led on to Vine and Matthews confirming that continental drift really happened, that the seafloor was spreading. That's the magnetic stripe story. This is the equivalent, but on land. On land is much more complicated than at sea, because at sea you've just got a simple tape recorder which opens up and records the current magnetic field. It ends up with a series like magnetic stripes. On land, things are much more complicated because you've got a multi-layer system. Next slide, please. So this is the results of our model, and basically it shows the intensity, the magnetic susceptibility, that's the magnetic intensity, that the computer thinks is happening at any particular part of the model. Okay, so this is the highest magnetic susceptibility here, 0.7 units, and it ranges down to 0.01. Below that, we can't really distinguish it from background. So the variation here is not very great, but you can see that the red zones there, they're the hottest part of it, of the system, if you like. And what we do see some reflection of the tectonic lineaments I talked about, like the Malvern lineament up through here. The Variscan front, south of London, is marked out by something. There's some termination of this big magnetic body here in south central England. This is at 10 kilometers depth. So it's just like a horizontal slice through our cake at 10-kilometer level inside the Earth. So you're looking inside the Earth and you're seeing all sorts of interesting features and signatures. When we go to 15 kilometers depth, we can see that this one has changed. It's become more continuous, but there are all sorts of circular features that are appearing within our main feature of interest, this one. And for the first time, something is appearing south of the Variscan front. Okay, next one, please. Now we go to 20 kilometers depth. And again, interesting features in our main body here. Again, all these things are varying continuously. And then at the deepest level, you can see that there's much more of the magnetic rocks, which have appeared as if by magic from beneath the deep cover, which here, in this area here, there's a thick Mesozoic sequence in the Wessex Basin, and then Carboniferous rocks and so on. So the magnetic basement is deeply buried here. It's much less deeply buried here. But what this processing is doing is bringing out the continuation of this stuff south of the Variscan front. Next slide, please. So those are horizontal sections at various depths. We can also slice the cake vertically with conventional, producing like geological sections, and we end up producing a feature like this. This is a south to north section, and we can see this is that main body in central England that's been producing the big magnetic anomaly, and you can see that it's sourced quite deep in the crust, but it has a sort of a strange prong to the north. Interesting features within it, little sort of like encastellations or something. And these are three parallel sections, three parallel south to north sections through that body. Next slide, please. VF will be Variscan front. Yeah. Yeah, could we just go back? Yeah, so I should have, yeah, so VF, here is the feature that's associated with the Variscan front. The thrust front is actually further north, so there's a detachment that goes up through here. So it's picking up the Variscan front, but that big drop down, and that was enough to effectively conceal these magnetic rocks, from the surface mapping. But it comes out on the computer modeling. Oh, okay. Well, that's into another terrain. That's into non-magnetic crust, but still pre-Cambrian crust. It's just another sort. If you like, we can regard all the coloured rocks here as components of the Charnian, whereas the other rocks are non-magnetic rocks that surround them. Next one, please. Now, I hope this works. What we're going to see here is a video. Now Gareth, on your laptop, can you click on this bottom border here, and then by magic a arrow should appear. Not there, just more here, in that sort of area. Bar should appear with a player symbol. Let's see that. I hope this is going to work. Good. Okay. What I did is I've synced this to in the Med Patrol model to a timer, and it's going down 1 kilometre every second. So we're dropping down now through the crust, deeper and deeper levels of the crust. We're now down to 20 kilometres, and we're seeing those interesting features, the circular features I was telling you about. And we're seeing that the magnetic anomaly extends way south of the Variscan front, and we can start to see some offsets in it as well, related to the tectonics. So we've reached 34 kilometers inside the Earth. You've got the coastline of Britain here, so hopefully you can see where you are. And we're going to go the other way. We're going to start going up through the crust. So we're now 30 kilometers and rising. And we're looking at the internal structure of the Earth. But do remember that this is a model. It's not actually like seismic data, which actually records an event within the structure. This is what the computer, the algorithm, thinks is there. I could make all sorts of jokes about grok and artificial intelligence, but it probably wouldn't be appropriate. So I won't do that. Here we are, back up at the surface again. And that's okay. The dashed lines are major tectonic lineaments. So the heavy ones are known features like the Variscan Front, the Morven Line, some structures in eastern England. But the dashed ones are things I've interpreted on from the model. So this is new structure here that we've learnt by doing this exercise. Yes, it would be. The Morven Line is here, so the Oxford Basin's in here. Yeah, and the Banbury borehole, Withycombe Farm, I think is situated about there somewhere. That has a very deep-seated structure, yeah. And then there's these interesting sort of circular things, which I shall come back to. Okay, so next slide.
On that model, was it a fairly arbitrary decision to decide 38 kilometres?
No, it wasn't.
Because the illustration doesn't necessarily seem to show the magnetic rocks ending at 38.
No, that's what it's modelled to. There is a Curie point where the rocks lose, with increasing temperature through the crust, the rocks lose their magnetic susceptibility. So that is like an artificial boundary, that bottom line there. And that's set as a parameter in the model. The reason that's set is you've got the Curie point and the rocks lose their magnetism, so the model's irrelevant. But also at that point, you've about got the moho anyway. That's about the depth of the moho under southern Britain. Conception of a physical model for what the Charnian terrain looks like. If you think, basically, if you think of a solid lump of magnetic material, it's not very magnetic, of course, in the Earth's crust, not as magnetic as an iron anvil. If you think of that forming the block that underpins the whole of southern Britain, and that's the cause of that magnetic anomaly. And then to the north, we've got this funny prong that sticks out. That's where the Pharaoh, of course, used to make the horseshoes. But that's the sort of analogy for this prong structure we've got in pointing up towards Wolverhampton and the Morven Line. So if you want to think, if you're having trouble grasping the model from the computer model, then think of an anvil, think of this block as your analogy for what's in the crust of southern Britain and for what's making it so strong. Thank you. Thank you very much. Next slide, please. I'll try not to be too violent. Here's a slightly different form of these magnetic maps. In this case, we produce structure maps. These are not slices at constant levels. These are now structural maps showing the depth to which these features form. So, for example, at a relatively low magnetic susceptibility, we've got it's at high points on here up towards Wolverhampton. This is this prong I was telling you about, moving away from the main block of the anvil, if you like. And the anvil has a sort of like a rift zone in the middle of it, this strange structure here. And then also these circular features that appear, which I'll tell you about. So next slide, please. And we probably don't need to look at that. That's just deeper still.
So where's that structure?
Yeah, it's probably Reading. Reading's down here somewhere. And it comes up to Banbury. Withycombe Farm is there. Withycombe Farm. So it's sort of central Oxfordshire, I suppose. Okay, next slide, please. It's here. It's over there. Yeah. Okay, next slide, please. So this is the model that we came up with based on that geophysical model. We came up with this interpretation that the Charnian domain, which is all the blue stuff here, is like a wedge. inserted into slightly older crust in southern Britain, and that the Charnian rocks themselves and the Nuneaton quarries, which some of you may have seen, they're within the Four-Arc basin of this system, whereas the rocks we looked at Kempsey Borehole and Netherton Borehole are in the Back Arc basin. Basically, when we have sedimentary basins, volcanic arcs are often associated with sedimentary basins, and the ones that are towards the trench we call the Four-Arc, and the ones behind the arc we call the Back Arc. So it's quite logical, really. And then they've also got these, and you can see that that feature extends right across the Variscan front. It's just concealed by the thickness of the Mesozoic and Carboniferous structures. And then on here I've marked various features, various offsets of the thing, which are old structures that we can relate to features in the Charnian, and also these white things here, which when I was writing the paper, I thought were caldera structures. And then, because you've got a volcanic arc here, so the natural thing is to have a chain of calderas running up and down it. But then John Donato reminded me that these actually are associated with circular gravity anomalies at Reading and elsewhere, and therefore they're more likely to be associated with granites. But the two things are virtually the same, because I bet every caldera has a granite batholith sitting underneath it. It's the way they form. So we were sort of half right, as it were. That's a Charnian rift with these calderas sitting on top of it and granites underneath those. But remember, most of this thing is quite basic. It's basaltic andesite. This is the core of the rift. You've got volcaniclastic rocks on either side. You've got mainly basic rocks in the center there, quite primitive ones, so really primitive marginal basin basalts, as primitive as anything in the West Pacific marginal basins today. They're more primitive than conventional mid-ocean ridge basalts. So that's the sort of core of the arc, but sitting within it are these calderas, which seem to have granites underpinning them. And a further consequence is we had to revise our boundaries of the Midland microcraton to better suit this geophysical model. So that's changed a bit as well. So yeah, for those of you that worry about things like where the boundary of the Midlands microcraton is, and the Anglo-Brabant Massif and the London platform, these are all tectonic features later in age than this, but it's our belief that these pre-Cambrian structures control these later structures. Next slide, please. No, we're not, but I'll tell you what we are going to see in the very next slides. It won't go on too much longer now. Next slide, please. Absolutely. Yes, that's exactly right. Exactly right. So North Island, New Zealand analogue. We're going from Britain, central Britain, 565 million years ago, to North Island, New Zealand, which again, some of you may have visited on holiday. Next slide, please. Here's the regional map. And you remember that we've got the Pacific Ring of Fire here, the subduction of the Pacific Plate all the way around. And New Zealand is just here on this boundary of the Australian Plate, with subduction of the Pacific Plate in general beneath the Australian Plate. Next slide, please. That was an image we showed before. So this is north in this direction, top end of North Island, and we've got the Australian Plate dipping in a subduction zone westwards beneath the Australian Plate. Next slide, please. And these lovely volcanoes, well, as I say, they're lovely photographs, but these volcanoes are deadly. This is White Island, which some of you may remember erupted, killing quite a few people in a tourist party in 2019. That's there, just off this blue wedge zone. And this is the beautiful, I can't remember if this is Tongariro or Ruapehu, but in the Taupo zone of volcanism that extends southwards through North Island, but eventually ends in a wedge. And just before COVID, I sort of started pulling all sorts. I made this connection between southern Britain and New Zealand, and realised that New Zealand explains many of the features that we see in southern Britain in the pre-Cambrian. Basically, the story from New Zealand is that we've got an offshore basin here. We've got the Pacific crust here, which is being subducted westwards beneath North Island. We've got an offshore marginal basin here with a trough, which penetrates southwards into North Island as this wedge of the Taupo volcanic zone. And basically, that volcanism is back arc extension related to subduction along that Kermadec trench offshore here. Further back, there's another zone called the Terrane Rift, which has got more evolved calcalkaline basalts in. Plus, these are mainly basalts and rhyolites. So there's some similarities with the crust as well, because this part of the Australian plate comprises hundreds of millions of years worth of accretion of greywackies on the margin of the Pacific Ocean. So the Pacific Ocean has existed for hundreds of millions of years. In all that time, it was accreting these greywacky strata onto the edge of the Australian plate. So there's no Precambrian in this part of it. There are some, I think, Ordovician rocks, but they're the oldest it goes. So the crust of North Island, New Zealand is quite juvenile. And that's the same sort of situation that was true of southern Britain 565 million years ago. Next slide, please. And if we look at this marine geophysical map, this just shows that trough extending northwards in the marginal basin. And these ridges here that are related to volcanism, and it's these that are driving into the Taupo zone like a wedge into the continental crust, crossing from the ocean boundary onto the continent. And that is my analogy for Charnwood. Next slide, please. Because if we do some gymnastics, graphic gymnastics, and we do a latitudinal mirror flip of New Zealand, we can turn it upside down. This is the north coast. We now flipped it, and you can see in my model that the Taupo zone is now coming in from the south, not the north, or apparently from the south, and that is analogous to my Charnian wedge here. We've got the subduction zone off here, and in southern Britain it would have been somewhere off here in the southern North Sea. And then behind that we've got another rift, the Taranaki rift, which is analogous, I think, to the structures that contain the Ukrainian lavas and so on west of the Malverns. But the point is that the blue stuff and the green stuff, they're the same age. It's all about 570 to 565 million years. It's all part of the same system. It's just that the Charnian is a marginal basin penetrating into the older crust, whereas west of the Malverns, we've got the older crust, and then you rift that to form these extensional basins that have, for example, the Uriconian and volcanics in South Wales. They're all about 565 million years old. It's all part of the same extensional system, not accretion. Okay, next slide, please. So now we're getting on, we're almost there. Shame we're losing this off the, won't worry too much about that. This is basically just a slide to show us that there was an old paleocontinent. You probably know of a paleocontinent called Gondwana. There was another one called Rodinia that incorporated bits of Gondwana and so on. That all broke up about 700. Oh, thank you very much. That's splendid. Service, tectonics works. So 720 million years ago, just before the period we're interested in, this old paleocontinent called Rodinia broke up. You can see that you've got bits of it here. You've got, I think Australia is in the northern hemisphere. Laurentia is about on the equator, and Amazonia and the Baltic area, for example, Norway, Sweden, much of Northern Europe, that's all down south of the equator. And Britain originated in this area here, somewhere down here, between Amazonia and Africa. So the disposition of the continents and the oceans was completely different 565 million years ago. And not only that, Britain actually was 60 degrees south rather than at 52 north. So it's moved all that distance in that time. It's all been done by plate tectonics and continental drift. Next slide, please. So this is asking to move everything. Again, no, we don't need to. Don't need to. Don't. Yes, good idea. I've also broken the controller. There we go. No, next slide, please, Graham. Gareth. I like this reconstruction because it actually has Britain turned around. So we've got Gondwana lying to the south with its various components. Somewhere in here, there it is, SE, that's southern England. It's got Britain turned around about 180 degrees to its present orientation in the southern hemisphere. And there is actually paleomagnetic evidence from the declinations that Britain has suffered a 180 degree rotation. Southern Britain has suffered that degree rotation since the times I'm talking about. Next slide. So speculatively, I turn Britain through 180 degrees, and now I match what would have been the New Zealand equivalent of that. So basically the subduction zone would be westwards in present coordinates over here to fit that reconstruction. Next slide, please. Okay, and then a more regional reconstruction, again with Britain turned, pointing the wrong way, pointing southwards towards the South Pole with a wedge coming in. That's my reconstruction for how things were in latest pre-Cambrian to early Cambrian times. A sea of little microcontinents on the edge of the Iapetus Ocean, floating between Baltica and Africa and Amazonia. Next slide, please. Okay, some conclusions. So we produced this new model for the development of southern Britain. I'm a lot happier with it, and it implies much more extensional tectonics than accretion tectonics in the formation. So that's quite a sort of a paradigm shift, as it were. We've done an inversion of vintage aeromagnetic data, so getting new insights on internal crustal structure, or what we think is internal crustal structure, using these old data from 1965. No, you could do modelling, but you wouldn't get the same story. The gravity is mainly picking up the sedimentary basins, in particular the younger ones, because the density of the rocks is much lower in those. So you're actually getting, you could do the modelling, but you'd get a sort of a much more, a shallower overprint, as it were. What we're looking at with the magnetics is the deeper structure. We've seen that the deposition of the volcaniclastic strata with their important biota, the Charnian biota, occurred in fore arcs and back arc marginal basins bounding a Charnian arc, which is a rather primitive thing with basaltic andesites. Has a rift in the middle, and it seems to have these caldera or granites associated with it. And that's contemporary. The development of that blue zone, as it were, was contemporary with rift sequences west of the Morvens. For example, the Uriconian, Longmindian, and South Wales, these things that you may have visited on field trips. The significant geochemical and structural variation observed in a small region of crust in southern Britain is replicated in the modern analogue in North Island, New Zealand. In other words, the size of this thing is virtually comparable between the Precambrian rocks and the more recent rocks in New Zealand. And I think the processes that were involved in its formation is pretty much the same. And I think this model explains better the unusual geophysical properties and mechanical behavior of those subsequent structures like the well, the Worcester Basin, how that's behaved, the Anglo-Brabant Massif, the London platform, all these, this terminology of structures that has developed over time to the recent period. All of these things are controlled to some extent by this deeper Precambrian structure. Okay, next slide. And this is actually the film again. This is just to run through. So at this point, I would take questions, but I'm quite happy if once the questions are over, if people want to see the video again, the movie, I'll run through it again.